fine. And our three panelists' names and our cool little graphic there. And then a question to start that we already have. So as we're waiting for, yeah, we're getting better numbers, so we'll wait another minute and see. But I typically ask in advance this question, unless we come up with a different one. What's the one best advice you want to give our audience? So just something to kind of kick us off, and you can see what each of our three expert panelists have said for answers, which I really like. And I like the diversity of the answers as well. It's really great. Oh yeah, we're still climbing well. So we'll do intros in just a minute, folks, as we get going, probably one more minute and that'll be it. And so we thank you all for attending. We wouldn't be doing this if it weren't for you, if there was no one here. The four of us might have a nice conversation, but we also might have other things to do. So we're really here for you all. So we're gonna have a great conversation to start, probably 40 to 45 minutes, something like that. But use the Q&A function for your questions. You wanna say hi, that sort of stuff. Awesome, we love it. You know, where are you calling in from, etc. Do that in the chat, if you will, but you know how the chat is, it'll scroll way up. But your questions that you would like the panelists to answer in our, as the Car Talk guys used to say, in the third half of the show, post those in the Q&A. Nice. Who didn't love Car Talk? If you ever listened.
Great program.
Right? Oh my God, those guys were awesome. So a really quick Hazwapper, Hazmat, Car Talk story. I was teaching a hazmat class, right? So responder class for a bunch of guys in Southern, you'll appreciate this, John, in Southern New Hampshire. And first day, hey, tell me who you are, what you do, and what you want to know. And this guy introduces himself, and he says, hi, you know, it's like the third guy or whatever. Hi, my name is Ray Magliazzi, and I drive the propane trucks, and I'm a deliverer, and I hope to understand better how to stop, you know, a leak in an emergency situation, et cetera, et cetera. And I just said, what a neat name. You know, there's one of the Car Talk guys is also named Ray Magliazzi. And the guy had an interesting look on his face that to this day, I'm still not sure. Like, maybe I'm tired of hearing this. His response, yeah, I know. He's my uncle. And I was like, well, that's really cool. But I then quickly moved on. I think after a while, I mean, it's like, oh, Johnny Klein, aren't your older brother and sister, you know, blah, blah, blah. And you go, you know, yes, Miss Canine, yes. That, you know, you just get tired of that, right? The youngest child, so him, the nephew syndrome. Anyway, so much for, you know, my little stories. Was Car Talk only in New England? Oh my goodness, no, Peter. No, Car Talk, the guys were based in Boston and Cambridge. They both went to MIT. These guys were incredibly brilliant. It was just amazing. And they were, I don't know, John, you know, you were a fan. I think they were amongst the most humble and funny experts I have ever come upon.
Definitely.
Yeah, and it was syndicated through usually the NPR stations. But you can go on, I think it's cars.com, and find Car Talk and still listen to them. Sadly, Tommy passed away, I think complications from Alzheimer's, which is very, very sad for all of us. But the two guys were amazing, and it wasn't all about car repair either. It was just great. Anyway, let's get started. Enough about that. Welcome to not Car Talk, but evaluating hazardous chemical reactions. Hey, it's water cooler chat for a reason, folks, right? You never know what you're gonna get. And I'm gonna stop the share of the slides so that people can see everyone's faces, because we have nice panelists here. So let's do some intros, and I'm merely our host moderator, Jonathan Klein, very happy to be here, Director of Risk Management and Safety Education for BioRAFT, and an EHS survivor of 33, 34, 35 years. I don't know. I think I should stop counting at this point, but really happy to be here and doing this. And I guess I'll go this way. And so on my screen, Katie, you are up. So if you don't mind doing your brief intro, that would be great. And you have, all three of you have such interesting expertise and backgrounds. I really want people to hear these.
Okay, great. Sure, happy to start. My name is Katie Mulligan, and I work at the Dow Chemical Company in an R&D group that we call within Dow Reactive Chemicals.
Mm.
And my background is that I'm a PhD chemist. So before joining Dow, I did not work in the field of reactive chemistry, but I like to call this role as kind of getting a second PhD, trial by fire, right? But of course, excellent training by my coworkers and colleagues. But what I like to think about it is I help for process owners from the small scale, so discovery scale, all the way to full scale manufacturing to identify reactive chemistry risks and hazards, and then use our laboratory scale equipment to help quantify the extent of the hazards by understanding the potential for energy release, both the amount of energy release, right, and the kinetics associated with that.
Nice. I mean, I heard reactive chemical group and I thought that's a perfect title for this. That's awesome. Great. All right, John.
Hi, I'm John Eisenberg, Associate Principal with Arup. I'm based in our Boston office. We're a global consulting and engineering company based in London, England, but with offices in 5 geographies across the world. I lead our science business in the Americas region, and I lead a team at Arup within our science business that does process hazards consulting. My background is chemical engineering with Shipley Company, which became Roman Haas and is now, well, went to Dow and then is now DuPont. Long road there. I was the pilot plant manager out there in the 90s in Marlborough, Massachusetts. And then I went into fire and risk. So my master's is in fire engineering. So we kind of combine those in our team here at Arup.
Cool. And Arup is A-R-U-P in case people are curious on the spelling and didn't notice it on the slide, right?
Thanks, John. Yes.
Yeah, no worries. I know how it is. And the whole, company changing. I worked for Balsam Environmental Consultants, and they got bought out by Dames and Moore, who got bought out by URS, who got bought out by AECOM. So I'm with you all on that. Yeah. And last but not least, please, Amanda, intro yourself.
So my name is Amanda Hoyt. I'm a health and safety specialist for the School of Molecular Sciences at Arizona State University. I got my thesis master's in organic chemistry, and at the time I was researching there, most of the group's chemistry, it was methodology focused, but we did a lot of our work with organolithiums, especially tert-butyllithium. And I took an interest in safety there. And started at ASU in their engineering schools, doing a lot of hazard assessments for chemicals and processes there. And for almost 2 years, been working with School of Molecular Sciences, which is chemistry and biochemistry department.
Yeah.
So a lot of academic research.
And full disclosure, Amanda and I used to work together. I worked at Arizona State, and Amanda and I were the Office of Health and Safety. And it was an interesting, and I will absolutely say, fun time. And I feel like I learned a lot from Amanda on this. And it was great having her there. So let's get started on some of these questions. So I think one of the problem statements is, how do we get people to even recognize that they probably, just as a best or better practice, to actually come to us and talk to us about things, talk to you all. So how do you help your people know when they should ask? Because maybe they don't want to always ask and they don't even know. So let's just start with that. And I guess I'll start in the reverse order. Amanda, do you mind starting us off, please?
So my guidance has usually been to students, if you read the SDS and it says not known to be a hazardous substance or mixture, then okay, that's probably something that we don't necessarily need to see. But if it does have hazards listed, then it's a good idea to run it past us, because it's very helpful to have a second set of eyes. And the students are not really that experienced at knowing, what needs to be looked at. So just any hazard listed.
A great way to start. Yeah. And that made a lot of sense too. And, sometimes we work with different people. Arizona State grad students, very, very smart, but don't have necessarily a lot of experience. Whereas, John and Katie perhaps are working with more mature, longer term scientists. So again, I said reverse order. So John, what about you next? And then Katie.
So it's definitely part of the safety culture. I agree, Amanda. And what I would suggest, right, is to look at things operationally. So, when we have a new process in a laboratory, the first question is, what scale is it at? Are we talking bench scale or process development scale or pilot? What size equipment and all of that. But even if it's not reaction chemistry, we also ask questions like, is there a heat of solution involved? And then what are the characteristics of the materials as well? So yeah, just enough to prompt some thinking, amongst the user group about, hazards in general, and make them consider things that they might not otherwise have thought of.
Cool. No, I think that's great. And Katie, what about from your experience at Dow?
Yeah, so it Dow, Jonathan, I feel like you hit the nail on the head. All researchers and all Dow personnel, right? There is an expectation that before any new chemistry is carried out, and that is even before a chemical is purchased and brought on site, that there is a hazard review that is conducted, and based on whatever type of activity you're going to perform, and that might be a chemical workup, right? A discovery scale chemical workup. That might be that might be not doing any reactive chemistry. That might be just bringing new chemicals in. It might be using the same chemicals in different ways. But whatever that is, if there are specific hazards associated with that chemical, or whatever that process is or that equipment is, then we have some internally developed and readily available resources to help guide researchers understand what they can and can't do with a certain review level. So the higher the hazards, right, the more sophisticated and more people generally with different expertises that need to be brought in to help perform basically a hazard assessment to make sure that the hazards are well identified and then properly mitigated. But I love Amanda's answer. Really, if you're talking about a chemical, I think starting with SDS is step one, no question.
Cool. Well, let's get into an area that I know I have always struggled with. So, researchers, whether it's at a university or whether it's trying to do cutting edge science in industry, are trying to innovate. And if you're innovate means new. It doesn't mean repeat old stuff. So they're always trying to find that new niche thing. As a matter of fact, a researcher getting a PhD has to do something that no one else has ever done. Now, that's why these get very, very niche. So how do you evaluate the risks, right? Not whether it's safe or not, but the risks when the process or the new chemicals, there's I will say almost no data on it, or none maybe that are obvious to the people like me that don't have the depth and breadth that you all do. And I'll mix it up and say, John, why don't you lead us off on this?
Sure. So I would think of it in terms of classes of materials. So, even if the particular chemical or process has not been done before, we likely have some good data and safety history on the specific classes of materials that are going to be used. And I know we'll get to this a little bit later, but is there a catalyst involved? And what type of catalyst is that? You're presumably running in the liquid phase, but for your reaction. But then what are the other unit ops that are present there? Will you need a condenser? All those types of questions. And I think we can narrow down from that into, okay, what do we already know? Are these flammable liquids? Are there unstable materials there? Are there water reactive materials being used? And so we can start grouping the relative hazards and then figure out, okay, what facility do we need and what mitigations need to be in place to house this type of new chemistry.
Good, great, yeah, great start. I'll go to Katie next, and then Amanda, of course.
I echo what John said. I think that it's very important when you're doing really new novel chemistry to balance. Yes, this is new chemistry, it's discovery, but how new is it really? Can you go out into the literature and find existing resources or reports for similar, right, analogous type chemistries or reactions or even equipment, right? Even if it's new equipment to you, does that mean it's completely new? Right? Go and see what you can find out there. And I think that maybe that there may be a bit of a gap or a void for a lot of people in all walks of kind of in laboratory work, right? From academic and even to industrial, is understanding that there are resources out there that have worked to group the hazards associated with certain chemical, common laboratory equipment and common chemical types or families, and that even if you're doing something that is novel and new, that you're likely to be able to find some sort of information around chemical compatibility or even reaction kinetics for for that type of chemistry. But knowing where to find that information can be difficult because you don't see a lot of chemical safety taught in the typical, I think it's certainly undergraduate curriculum in the physical sciences.
Yeah, a problem that I think a lot of us know and still struggle with. All right, cool. And Amanda, what else would you like to add?
What John and Katie have said is also really good. The only thing I could add is, I do more of the looking for similar chemicals and similar reactions. From my organic chemistry background, I try to look more like, what functional groups are there, and then see if there's anything similar that maybe has just a longer or a shorter carbon chain, something that might be on a glove compatibility chart somewhere, or just have more data on its reactivity just based on the rest of the structure, the functional groups.
Cool. No, I think that's great. I didn't mean to cut you off there. I thought you were ending. So I want to actually ask Amanda a follow-up question. There's always questions for the group and for each other, but people are free to chime in. So are there specific or general hazardous chemical reactions that do come to mind from your experiences in engineering and molecular sciences?
Most often what I've come across is a underestimating of oxidizers in a reaction. I don't know if that's just sort of like a gap in just general chemical education, but they don't often, really connect that, if something is an oxidizer, that it could be reacting with other things in the mixture. And that kind of showed up in the infamous case that I think it was, it might have been in England or in Europe, but at the school, the student accidentally had one of their oxidizers reacting with the reaction solvent to make a unstable explosive byproduct instead of reacting with the stuff that they had put into the solvent that was supposed to be the main part of the reaction. And I do see quite frequently that, people that are working with nitric acid, they're just thinking of it as one of the 6 strong acids rather than thinking, oh, this is an oxidizing acid. So that's probably the most common.
Cool.
Underestimated.
No, I think that's great. John or Katie, did you want to add anything onto that, or shall I go on with your questions?
Go ahead, Katie. I have something as well.
There are quite a few kind of different chemistries or chemical types that give me pause, and one of those is just the kind of whole category, and it's wide ranging, of high energy materials. And so Amanda mentioned earlier this, the idea of using functional group recognition or chemical moiety recognition to understand how a certain chemical, even if it's a new-ish chemical that's not well characterized, to understand how it might behave. But high energy materials, right, those are the class of materials that can rapidly decompose and evolve energy and oftentimes, right, pressure as well, right, generate pressure very rapidly, right, because of that, because of that decomposition that's often thermally generated. So I think that, so that includes, chemicals that have lots of nitrogens, especially nitrogens bonded to other nitrogens, right? That includes any peroxides, both, especially organic peroxides. But if someone asks me, what are the types of chemicals that really, or chemical reactions that concern me, ones that deal with pyrophorics and ones that deal with high energy materials.
Cool. And John, you said you did want to chime in as well. And I've actually got a very brief peroxide micro story that I'll share after you're done, John.
So when I was in manufacturing, we were dealing with these exact issues. I mean, we used paraformaldehyde and formaldehyde as a raw material. We had to be really aware and have systems in place for storing those materials because, like you said, those, they're peroxide formers. Under certain conditions, whether it's aging or whether it's temperature or both, you can wind up with peroxides that you were not expecting, like you mentioned, Amanda. And Katie, I think you mentioned one other class of materials that I would agree completely. Some of these, trimethyl gallium, trimethylindium, trimethyl aluminum, those types of families of materials can give you a lot of surprises. They're very complicated to deal with because they fall into multiple hazard classes. They're unstable and a host of other issues. So, and I think it goes to your early point, Katie, about doing a PHA or hazard review, to start off with. And I think, oftentimes those aren't done exactly at the right time. And, because any facility that's going to utilize these types of materials needs to be designed accordingly, right? So we don't want to get into, all right, go use it and then do that, the hazard review, and then all of a sudden figure out that, your facility's not equipped.
Yeah. Yeah. And so for me, I used to teach HAZCOM, lab safety, fire safety, et cetera. When I teach the fire triangle and the role of oxygen, or in lab safety, what's an oxidizer? I used to work at a chemical transloading company, and we transloaded hydrogen peroxide that was concentrated at greater than 70%. So I can go get the peroxide out of my bathroom and gargle with it or pour it on a cut, and it's fine, right? But greater than 70%. And so as a training video, we showed the one from the maker, Axo Noble. And in it, you see a bare room, concrete, and a guy puts leather boots out in the middle of the floor, and he's all garbed up in PPE, and he takes the greater than 70% and he pours it on the leather boots, and you watch, and within seconds they smolder, they smoke, and then they burst into flame. There's just so much oxygen, and it's generating heat, for the ignition source, and leather, of course, is combustible. And so it's a great illustration of a lot of these, really very, very basic concepts. But let's keep plowing on. This is great conversation. The Q&A is building up. Amanda, go ahead.
If anybody wants a similar visualization, there's it was on there for many years on YouTube, probably still is, but if you just look for nitrile gloves with nitric acid, and they show just sprinkling a few drops of like red fuming nitric acid, and within seconds the gloves go up in flames.
Yeah, good one. Well, let's talk about protection, John. So this was one that I think I wanted to ask you. So the layers of protection approach, we like redundancies. As a colleague of mine used to tell his students when we both taught, hey, safety professionals, I wear both a belt and suspenders, right? So we don't want to rely on just one. So what about layers of protection and that approach for what we're talking about here when we're not 100% sure of exactly the reactivity, the energy, the thermal, exothermic, someone asked about, et cetera. can you speak about that, the challenges and what you've seen successfully? And then, if Katie and Amanda would like to chime in too.
Sure. So, starting at the lab scale, where, I think the focus of this conversation is, we talk about ventilation, presuming we're in a fume hood, but, what type of hood, what size hood, what size is the equipment, and then we look at ignition sources. Do we have grounding and bonding available? Are we what type of reaction solvent are we working with? Is it polar, so dissipates charge quickly, or is it non-polar? Like heptane, I think, is the classic example, that you literally can see a blue halo of charge at certain agitation rates for heptane in glass equipment. And how do you deal with that? There are definitely measures to take to deal with that type of hazard. So you sort of get the ignition, the ventilation, spill control, and secondary containment. What happens if you have a failure of your equipment? What are you looking at here? Is it a flammable liquid issue? Is it a flammable plus corrosive issue? Is it an off-gassing problem? And then what are your systems designed to be able to handle? So when we look at layers of protection, we're like, okay, we have ventilation, but is that ventilation on, at least standby power? So in the event that you lose primary power, that system keeps running. Do you have a redundant fan that's serving your labs and your hoods? I mentioned grounding and bonding. That system has to be checked periodically, not only for continuity but for resistivity, to make sure that you're effectively dissipating charge. I mentioned looking at specific solvents and materials of construction for the equipment. There's a range of dielectric constants for solvents that are really valuable to look at. And I know sometimes the reaction solvent is, okay, it has to be this, but we often get into conversations, could you use a reaction solvent that is, if not very polar, but more polar than heptane or hexane?
Sure, great.
So you end up with these layers, right? And we, depending on the situation, sometimes we do vapor detection. We have relative humidity control to try to deal with static issues, and you roll all this up, right? And you can actually calculate a rate of failure of these systems. So you can show it qualitatively and say, okay, I've got 6 layers of protection, and all of these 6 layers would have to fail for me to get an ignition or some other,
right, the so-called Swiss cheese model, right?
Right.
Yeah.
And then you could actually roll it up and figure out what's the aggregate probability of failure of all of your mitigation systems.
Great. Okay, Katie, did you want to add to that? And then Amanda, if you want to add, or we can keep going.
Yeah, I would. I love layers of protection analysis. I really enjoy taking the kind of the concepts that I've learned from my experience in supporting manufacturing operations and bringing that kind of mindset and methodology back to the lab scale, the R&D scale. And one thing I like to focus on when discussing protection layers with researchers and process owners for the small scale is that there are different types of protection layers, and some of them are more robust than others. And explaining that to people, and also going a little deeper and talking about, well, these are the protection layers that you're going to try and use to prevent, right, an event from occurring, right? And those I like to call the preventative ones, right? And then there are the protection layers that you put in place in the event that in order to mitigate the incident, right, to reduce the consequence to an acceptable level, right? And ideally, right, it's best to, if you can, prevent the incident. But in the event that you cannot prevent it, then you need to make sure it's mitigated. That way, the outcome is not a injury or a complete equipment loss or things of that nature.
Great. Okay, and Amanda, anything to add on as well?
With the layers of protection, I often just go with the the layers of protection that people would normally be using, but if it's an unknown, to just take an overabundance of caution at each of those levels. So, going with the smallest scale, going with maybe extra PPE versus what you would normally wear, even going so far as to test some of the properties of the material that you're working with, if it's something new, to see if it's going to pass through the gloves. Because if it's not on a compatibility chart or you're not sure, then it may just be the time to go ahead and put some of that, on or in a glove and watch it and see what happens.
Great, cool. All right, so we talk a lot about what do we know and how do we know it and all of that, but sometimes we get tripped up by what we think we know, but it's actually a myth. So I want to ask Katie first, and the others can, of course, chime in. So within this topic area at large, what are some of the myths that people may think, oh yeah, no, this takes care of blah, 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 but really it's not a good approach or it's just flat out wrong?
Yeah, I think there are quite a few myths that we would all like to bust this afternoon. One of my kind of pet peeve myths is that this idea that I feel like is rampant sometimes is that small scale is inherently safe. And it is, while it is true that a researcher, performing a specific chemistry on the bench scale that's generally less hazardous than doing or performing that same chemistry at the pilot or a full scale, right, the manufacturing plant. But that there have been plenty of reported incidents in academic labs, industrial labs, and even school demonstrations where just small amounts of chemicals have led to uncontrolled reactions, fires, explosions, right, injuries in the worst case. So having the small scale by itself, it's just not enough, right? For any process. You really do have to delve into it and determine the physical and chemical hazards and make sure that those hazards are, once they're identified, that they are then properly mitigated, right, so you can avoid the negative outcome.
Sure, and think in terms of, I was told students, a small amount, right, a beaker or flask or something of a very flammable or toxic liquid outside of a hood, it may seem like small, but it spreads out and all of a sudden you have a huge amount of surface area, which allows a lot more of the vapor phase to get into the air, breathe it in, or you get a spark or something like that. It's not the liquid, it's the vapor. So even a little bit of liquid can go a long way. And I'll go to Amanda and then to John. Amanda, anything to add on about any myths that you'd like to poke a pin in and blow up the balloon on?
Well, there's a few of them, but I guess one was an example of a student trying to clean something up with the same reagent that neutralizes it in a flask, and that you don't really want that sort of chemistry playing out on, the vinyl floor tiles of the lab. It did destroy the tiles. Basically, I think the student spilled, it was a reactive dye that was at least in their flask, it was neutralized with a little bit of nitric acid. And so they added gradually, greater and greater concentrations of the acid, trying to get the stain out of the tiles. And it just destroyed those. But when you spill something, you're not necessarily spilling out the exact amount. If you're needing to titrate that in order to react with it, then that's not something that's really feasible in a spill source situation. And even if you do, the stuff that you're adding to it, if it's not just water or some other I guess something that we can still use outside of a fume hood, then it's more likely to just make the problem larger.
Oh yeah, I remember that one. It was fascinating. I got copied into an email thread and the subject line was, "I'm sorry I ruined your floor," from the researcher to the PI. And you read the researcher's email notes and honest to God, it looked just like it had come out of a lab book, like he was doing an experiment on the floor. The spill kit was within feet of where it was and you go, okay, but anyway, let's move on from that. It's a great example though. I do love it. John, one myth in particular you'd like to bust on your own?
Sure, and it follows what Katie was saying. I think that, there's some realm of thinking that that says, okay, you do a chemical reaction in a lab, you understand the characteristics of your raw materials and you understand the characteristics of your end product, but what about the intermediates? What about the materials that are produced at different stages of the process? Could be different stages of the reaction, could be different stages of unit operations, could be filtration, could be drying, solvent drying, for example. And so what we've seen is really robust type of, hazard assessment programs. They look at the intermediates, they look at the byproducts, and they run thermal stability testing on those materials, and they see what the data looks like. And, do we need to mitigate hazards, in the middle of the, like I said, either the reaction or the overall processing.
Sure. Good. Great. Let's talk about catalysts, and then after that, or in stream of it, let's talk about energy release. Up to each of you, it's fine, but I'll start us off on catalysts. And so how do you see them being safely added, stored, the risk perceived correctly, et cetera? What's been your best or at least better practices with that, and any lessons learned? And I guess I'll start this time with Katie. I keep trying to mix it up, but I'm not keeping track.
So there are a lot of different types of catalysts out there. So I will I guess I will for a lot of the different Dow chemistries and technologies, the catalysts are pyrophoric, and I would say that the hazards of, even though the hazards of pyrophoric materials are well known, even if most incidents that occur, generally the hazard is not a completely hidden hazard, that there's awareness of whatever that hazard is, but it's still, when you're talking about something like pyrophorics, it's difficult to control the hazard well, unless you have a lot of experience and you're being extremely careful with how you're handling whatever the pyrophoric material is. I think a lot of other catalysts have different hazards, aren't necessarily kind of reactivity hazards. But one thing about catalysis chemistry is that they're great, right? They reduces the activation energy for whatever chemistry you want to do, and so it moves faster. That chemistry moves faster. But if that chemistry is that you're trying to do, right, is exothermic or gas generating, then the amount of catalyst that you have present in your reaction mixture, that can certainly, you could significantly change the kinetics if you change the amount of catalyst that's available. And by doing that, then you might not be able to balance, right, the heat removal that you need, or be able to prevent generating so much gas that you could possibly overpressure your system. So I think that's one real concern around catalytic chemistries.
Cool, thanks. Amanda, anything to add to that about catalysts or catalytic chemistry?
Yeah, well, catalysts and pyrophoric ones, I didn't usually think of what we added as being, necessarily catalytic, but it was, the operating force in the reaction. It was just, we added a, 1-to-1 mole ratio of it. But with the pyrophorics we were adding, it was really important to have the reaction chilled down from the start. And, it was a small scale, but we were adding this all dropwise, that you get this reagent in a syringe and you're adding it, you let a little drop go in there and you give it a chance to color change and equilibrate with the rest of the solution before you add another drop, and just keeping that, slow enough that's not able to run away. But if you're adding something in there and it has a quick overturn and it's doing a lot of stuff, then you may need to keep that amounts very small in comparison.
Cool. Yeah. Sounds like a very good approach. And John, anything to add too?
So our experience around catalysts is that many of them are shipped under inert conditions, in a tube, in a small cylinder, to inhibit, any kind of reaction or, degradation of the catalyst. They're stored typically, a lot of these are class 4. If you look at the NFPA hazard diamond, they're class 4 of one of those areas. Could be water reactive, could be pyrophoric, like Katie mentioned. So they are not stored in the lab typically. that we've seen. They're stored in a dedicated chemical storage room under special, conditions, might need to be in a special cabinet. And then our question is, in terms of the operations, how are they being added to the reactor? Is it a completely closed system? Hopefully, yes. Are the inert conditions maintained? Hopefully, yes. And how long does that catalyst take to be consumed? Those are all important questions for us to know.
Yeah, great, cool. This is great. I feel like I'm learning tremendously from this, which I always love. So like I said, let's now talk a little bit about energy and maybe exothermic if it's specific to heat, but there's other forms of energy that can be released. So there's types and how the velocity of it, how quickly this might happen and under what circumstances. And there's two questions that I think get at this in the chat. And hey, everyone, best if you put your technical questions in the Q&A, because in the chat, they just scroll away. But I did catch them. So one was interested in knowing about exothermic, such as Grignard and hydrogenations. And another one that was sort of a follow-up says, what about handling overpressure, which we've seen as problems, of course, in big ways and small. And again, for hydrogenation, and so glass panels, et cetera. How do you work out whether required and size? So there's plenty of, I will say, space for you to attack this question however you would like, okay? And
yep.
I think maybe it's, I don't know, Amanda's turn to go first. I'm not even sure at this point. So I need like a 3-sided die and keep rolling that. I don't think that's possible.
I think D&D, the smallest you get is like the 4-sided die there.
I think you're right.
I call that one the caltrop, because whenever you lose it, you step on one, then you know it's worse than a Lego.
There you go.
I did actually do a fair bit of work with the Grignard reagents before they started us on the pyrophorics when I was in grad school. And again, it's, adding that dropwise and trying to, keep the reaction cool if the conditions of that reaction allow for it. It really comes down to, if you remember the general chemistry reaction energy diagrams where, you have your starting materials up here and then you've got your product down here. The distance between, the starting material and the product is a pretty good indicator of how much energy you're going to be releasing in that reaction. And some, release more than others. And it's really mostly just a question of how quickly you allow that energy to release, how much you're allowing to react all at one time. And, if you've got a larger flask, then that's going to bleed heat off less easily, and it's going to have less space for gases to bubble out of it. So, figuring in the scale and just how much it can bleed off is important.
Cool, great. And I guess, I don't know who, John next, and then Katie, of course.
So I did see a question in the chat, and there might have been multiple ones on the hydrogenation side. So we do a lot of work in this area. We have many clients running hydrogenation reactions in their labs at various scales. So one of the questions dealt with deflagration venting, specifically of the lab or of the room. So deflagration venting does not work with hydrogen, and the reason is the flame speed is so high for hydrogen that it quickly transitions from a deflagration to a detonation, meaning that the flame front, there's always two parts of an explosion, right? There's a flame front and a pressure wave. In a deflagration, which is running at lower than the speed of sound, so subsonic basically, the pressure wave gets to your exterior wall or your blow-up panel first. But in a detonation, it's the opposite of that. It's supersonic, and that's the case with hydrogen. So by the time the pressure wave gets to the vent, the explosion's over. Damage is done. So what we do for hydrogen and hydrogenation would be, an example. We do the PHA for sure, because we've got to quantify, what the explosion hazard is. And if it's determined that we need to mitigate that, which is almost always the case, we do prevention. So basically hydrogen gas detection, flame detection in many cases as well, interlock to a purge ventilation, normally at you know, 10, 15, maybe 20% of the low explosive limit of hydrogen, you know, and that's really how we deal with it. There's all kinds of other mitigations you can do with restricted flow orifices, and you know, try to limit your hydrogen flow rate as best you can. So there's a whole, you know, laundry list of things that you can do, and be glad to talk about that, you know, offline anytime.
Great. And Katie, please.
Yeah, so I think what's kind of specifically to exothermic chemistries is not all chemistries that are going to be performed, but a good majority of them are going to be exothermic. And so you should always, you know, before performing any chemistries, you should try and calculate how much energy you think is going to be released based on the chemistry that you're trying to do, right? What's the chemical transformations? How are those bonds breaking and reforming? And there are some good resources that are available. And I can try and put some things in the chat here as we go along, but to help you try and estimate, right, through calculations. So just a desktop method of, for your chemistry, what is the energy release, right? And then from that energy release that you've kind of written down, then it's best, if you can, to try and calculate a theoretical worst case temperature rise, right? So for everything that you have in your reaction pot, right, whatever the size is, if all of that energy were to be released, then what's the temperature rise? And then use that as a guide to, well, you know, am I inherently safe? Is that temperature rise 5 degrees Celsius, so I have no issue? Or is that temperature rise 200 degrees Celsius? And if that's the case, then then you better have some protections in place to make sure that the rate of that energy release is such that it's not going to overwhelm your ability to cool the reaction system and get you into either you know, where you're boiling your reaction mixture, or worst case, where you start to decompose the chemicals that are in there and generate a lot of non-condensable gases and possibly overpressure your system.
Great. Great. Thank you all. Well, this is about the time when we transition. So we're going to be launching a poll here on topics, and there it is. Thank you very much, Matt. And so please do the poll. This is how we figure out what webinars we're going to do and what ones we think generate a lot of interest, etc. You'll probably see some new ones, maybe some ones we've polled before. And we just appreciate the input that we get from our entire audience on these. So please engage in the poll, including, would you be interested in being a panelist, or do you happen to know someone that you would recommend as being a panelist? Always very interested in both of those. So, and while we're doing that, you know, I think that our panelists have probably been looking at not only the chat, but the Q&A. I think we covered the things mostly in the chat. There was one, what do we mean by catalyst? I think we've talked about it. There's all sorts of types. Not all are equal, not all are dangerously reactive, etc. So it's kind of a comment, if you would. So I think we're good on the chat stuff, and we're going to move to the Q&A. And so I'm just going to get that out of my way, and hopefully everyone does the poll. So let's take a look at some of the questions. So here's one, and I feel like connected to this one. Brian asked, as a safety professional who's not a chemist, so I have 0 degrees in chemistry, and any courses I took are so long ago, I'm sure I've forgotten all of it, right? I get a lot of pushback from researchers to create SOPs for the more hazardous chemicals. And there were a few answers that other colleagues gave, but from the perspective of those of us who don't have the expertise that you all do, any bits of advice on trying to, and maybe it gets at degrees of risk. So, and I'll start out with John on this one.
Yeah, I mean, so one line of, there's a few lines of reasoning here, right? So one of them is that, you know, you need the robust safety program. You know, and codes and standards require things like hazardous materials inventory statements and, you know, HMIS and HMMP, the hazardous materials management plan for a facility. And that's not only for the facility, but it's for the first responders. So, you know, we don't want firefighters walking into, you know, hazardous chemistry, and they need to know what they're responding to, right? And then somebody from the facility who's knowledgeable is going to meet them. So all of that gets wrapped in, you know, to that type of thing. So, you know, I understand where the question's coming from, you know, because oftentimes researchers have been working with these materials, you know, for most of their lives. It doesn't guarantee that they've been doing it the correct way, though.
Yeah, I agree. I agree. Katie, go ahead. Looks like you're ready to jump into this one.
Yeah, what John just said really struck a chord with me. I think that's kind of another myth, is that if you have a mature or existing process that has been carried out multiple times, maybe even over the course of years with no incident, that just, that does not mean that there is no hazard or no risk with that process or with that chemistry. And so you could be essentially on the edge of a cliff potentially, and if one thing changes, then you could go over that cliff and an incident could occur. So I think there's a question about how do you get people to do something, and that is hard. It's not easy to do that, right? But one thing that you can do, right, as a safety professional is to show the value of something like an SOP, right? See if you can find some incidents that have occurred where an incident investigation occurred, and one of the findings was that an SOP could have prevented that said incident, right? So showing the value of whatever you're trying to put in place to the researchers, I think could go a long way there.
Great. Yeah, absolutely. And Amanda, what would you like to add on to that?
Yeah, it is important to have those SOPs around for emergency responders, because they'll be stepping into the situation cold. But it also really helps with training in new graduate students and keeping that process the same from one person to the next, because the PI may have this idea in their head of what the process is, and the graduate students that's been working with this a lot has their own very slightly modified process that they use that's got certain things set in a more convenient way for them that just works better for them. And then that graduate student is the one that's teaching the new person what this is. And then that from one student to the next, it very quickly becomes a game of telephone. And in one of the labs that I was working with that had an incident, the incident happened because the procedure had been handed down from one student to the next to the next. And that was their stated procedure in the lab, is that the most senior graduate student that's familiar with this procedure teaches the new people coming in. And they were using a process that had not been approved by the PI because it had deviated. And unless they have that in writing, then they're not going to know. So I would say if your PIs are pushing back, ask them if they still keep lab notebooks, or if they ask the graduate students to keep lab notebooks. If they believe in the value of writing those things down, then there is just as much value in writing down the process and making sure that it stays the same as what the PI intended it, and not
Right.
what it's evolved into after multiple generations of students.
Yeah, and not all students realize that the PI in the university owns the lab notebooks, not the individual researchers. It's not their personal property.
That's why it's good to get the ones with carbon copies.
Yeah, there you go. Yes. So there's a question about SDSs, and we've talked about that. And of course, that's I always used to say, a great place to start, but a lousy place to end or stop, right? There's always more. So, Joanne was curious, and Carmen did answer about proprietary processes will sometimes result in, as Joanne was asking, why does info on an SDS for a specific chemical vary sometimes from manufacturer to manufacturer? And there can be other reasons too, but I'll just tag on to that in the chat. Michael was asking about references to resources, quick calculations on energy of reaction, a term of art that I know you all know and understand better than me. And he adds often calorimetry, if I got that pronunciation right, data isn't available, so any good sources. So again, go in whatever direction you want, but we have sometimes not enough sources, and sometimes we have so many sources that they're really overwhelming. So maybe what are the best? What's your briefly, of course, time is always a thief here, recommendations in this area? And I'll start with Katie this time.
Sorry, Jonathan, can you, what was the actual question again that was in the chat? Is
In the
around,
chat,
what happens if you don't, how do you understand how much energy could be released if you don't have like, laboratory scale like calorimetry tools?
Yeah, let me just read it. Can you provide references for quick calculations on energy of reaction? Often calorimetry, whatever.
Calorimetry.
Calorimetry data isn't available in any good sources. Does that help?
Yeah. Yeah, so I can do that. I can do it through the chat. So there are a couple of published papers, actually more than just a couple, around how to calculate the theoretical heat of reaction. Right? And but in particular, when you're talking about chemical research, a lot of times you can't go and look up that chemical reaction. But you know, thermodynamics, right, it's in certain chemicals they act very similarly. So you could go and find analogous chemicals, write down analogous chemical reactions, and use available thermodynamic tabulated data. So heats of formation or bond energies, right, to calculate a theoretical heat of reaction. And that is my recommendation if you don't have any calorimetry at hand.
And it looks like Stuart has put in the chat good references, Breathric's Handbook of Reactive Chemical Hazards. So,
yes, Breathric's is excellent for that. I mean, but if you're looking for tabulated thermodynamic data, then there's the NBS tables, there's like the CRC handbook, there's the NIST webbook. Those are great sources of information for tabulated thermodynamic data.
We'll try, and what we'll do is if our experts, and we'll look at the chat and everything else, and if you all don't mind, shoot me an email with your list, and we will compile it all into one and get that posted on the site for folks. John, and then Amanda, anything to add to this area?
I would agree with everything that Katie said. I think, that you can calculate it for sure. If you know some of the property data, should be able to figure out heat of reaction, and then look at what scale you're running this at, and what's the batch size and so on. I wanted to also just briefly speak to your point that you brought up right before that, which was the SDS, and the inconsistency of detail in various SDS. So, there is that old reference SAX, SAX, that we've utilized quite a bit. You can go there. It doesn't line up exactly like with the model codes and standards or the NFPA, diamond, but it does, give you some pretty good data where you can, derive what the hazard really is of the material. And they have, if you're dealing with a trade name, and they don't want to disclose what the major constituent is, there are some databases that have, trade names in them as well that you can utilize.
Great, this is great. And Amanda, please, anything you'd like to add?
Nothing to add on the energy calculations, but referring to the SDS inconsistencies, I often just go for looking at as many SDSs as I can, especially if I'm finding that some of them have different information. Then I just start to try and pull more from just any company I can find that has put out any SDS on this type of material, and just sort of try to get a feel for, what they seem to be reacting to. Is it only, in a certain percentage of concentration range where this is happening, or is it all across the board? And just take all the precautions into account as a sort of just in case, this SDS writer knows something that somebody else didn't, that we still take that into account.
Great. Well, we're almost on the hour. If our panelists are able to stay for up to another 15, that's great. We'll continue answering as many of the questions in the Q&A as we can. That's great. If our attendees can stay, please do. If you have another commitment, we understand, and we're sorry to see you leave. The recording, as someone did ask, is always going to be available. It takes us a little while to do any fine editing. We don't redact or take out major parts or anything like that, don't worry. And then get it posted on our site and on our YouTube channel as well. So give us a day or so, and that will get posted definitely, and you get to watch the rest. You're quite welcome. Jill, happy to do so, and Dina. And further to our conversation about this and chemical evaluation and reactions, The next webinar in a couple of weeks will be chemical safety for non-chemical hygiene officers. So that one should kind of pick up where this one is leaving off. And then 2 weeks after that, on the 23rd of September, better practices for onboarding new scientists, researchers, scientists, PIs, and others. And then in October, on the 7th, as I mentioned during the water cooler chat, the Delta variant, weathering the storm. Are you? And how is that going? And what are people doing? So trying to come up with a good diversity of topics here. And let me quickly also look at Menti if I can and see, oh, let me share this real quickly here. Sorry, folks, and show you what everyone has posted for the Menti most hazardous chemical or reaction that they have seen. There's all sorts of them, some zinc, something with ethylene.
Diethyl zinc.
Diethyl
That was a pyrophoric.
It's organometallic, yeah.
Maybe I'll let
Difficult
you
to deal
guys
with.
figure these out. Chlorine trifluoride sounds exceptionally bad. Yeah, and I know the one that Amanda was referencing, I think it was in the UK at Bristol University, and Amanda, was it TATP?
Yeah, formation of TATP by the hydrogen peroxide reacting with not the main reactant, but the solvent.
Was it acetone? Probably it was acetone. I mean,
yeah, and that one ended well. No one actually got hurt, no explosion. The researcher stopped, called the PI. The PI said, don't do anything, got EHS. They called in the bomb squad, et cetera. They evacuated, of course. Everything went well. I will say, having good culture of safety and psychological safety for everyone involved, that they know they can speak up even when, oh crap, what have I done, happens, can save the day. That can make the entirety of the difference. All right.
Favorite thing about that one was that the safety culture was further reinforced by the dean of the school, saying, you know, just commending the student for bringing this to the appropriate, through the appropriate channels as soon as they noticed it. Yep. They didn't do anything to try to mitigate it themselves or cover it up. They just went for help, and, you know, they were supported.
Yeah, great.
It was a good thing to see.
It really was. It really
I love
was.
that response in the chat there. Someone said combustion of gas in their VW Bug. That was awesome.
I love it. having owned a VW Bug, I appreciate that one very much. All right, so Lisa asks, and I know Amanda and the others have good experience with this, any recommendations on best practices for storing water reactive chemicals, especially when the outside environment is typically humid? So an added level of complexity, and because I know Amanda has a lot of experience here, I'll start with Amanda.
Parafilm. Just wrap or, you know, sometimes electrical tape I've seen also used, but I think parafilm sort of sinks into the crevices a little bit better. You do have to keep that away from anything, from any of your acetone, because acetone will dissolve it. And from what I understand, isopropanol is pretty good at washing that stuff away as well. So, you know, just to protect that seals, but, you know, just I've actually cleaning out some of the older labs, I've been finding, you know, what they used to use before parafilm, and that's just basically jars full of pellets of paraffin wax, and they would, you know, melt that and, you know, dip bottlenecks into that to seal them off before parafilm. But yeah, just seal those necks as much as you can, secondary containment, and then wrap the neck of that so that nothing can get in through the lid, the cap, and the jar interface.
Cool. Katie, what about you? Anything to add to what Amanda's already mentioned?
Not too much. I think that's you know, it's an interesting commentary on the right material of construction. Right? If you're you know, certain solvents, right, certain chemicals, you know, the vapors, they don't play well with other, you know, with kind of, you know, gasket materials, or even kind of even, you know, a cap. So certain water and air reactive materials don't come in, you know, the sure seal type bottles, right, that are kind of self-sealing and resealing, even though those can degrade over time. So be careful of that. But you know, you do always want to be cognizant of the choice of the material of construction for your chemical.
Cool. Great. And John, anything to add too, please?
A couple of things. So one is, what is a closed system versus what is an open system? How many of us have walked into a lab and you can smell solvent? That would be a good indicator that, as Amanda pointed out, there's a lot of parafilm going on and there's some aluminum foil going on to try to close quote unquote connections between equipment. So, we've advanced to the point where there are now specialized, caps and everything for solvent bottles, and it's a strictly closed system. The other quick thing is if you're running a reaction under vacuum, which it can be the case, or you're pulling vacuum on a solvent drying operation in a lab, be very cognizant of where that solvent pump, the vacuum pump exhaust is going. Really needs to either be, should be right above, the hood with a hard connection into the exhaust line and duct. But unfortunately, we've had some instances where, someone puts a piece of tubing off of the vacuum pump exhaust and they're literally exhausting vapors into some interstitial space behind the hood or in between hoods, or, with at times catastrophic results. So
yeah, no, I totally get it. Thanks, John. So scrolling through the Q&A, trying to figure out what questions have we kind of touched upon and which ones haven't. So we've touched upon acids a bit, in particular nitric, a bad boy if there ever was, but there are others. And so, Lisa asked, can we expand more on nitric acid reactions and storage? And then Margaret asked, sort of piggyback on that. And also, what about the lesser known dangerous hazards? And Margaret listed HF, which I'm sadly familiar with, not personal exposure, but others. And I would add on to that perhaps even acetic, which isn't perhaps as common or as the risks appreciated. So again, really acids, the risks, they may not be perceived really well. Feel free to go in whatever direction you want. And to mix it up, I'll go to John first. I don't think I've started with John for a while, so.
I'm sorry, your question. I was reading the reading the Q&A, but is your question specific to HF, or is your question?
No. So more broadly, you got HF, you got nitric, and nitric can be red, white, fuming, blah 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 blah, right? Acetic, there's concentration, there's molarity. So there's a lot of different factors to juggle. Sometimes we understand it, maybe non-organic chemists don't. Etc. And we maybe appreciate the risk and maybe we don't appreciate the risk. I know someone personally who did not appreciate the risk of nitric and paid incredibly dearly for it. So I think that gives you a broad area. Pick a slice, go for it. We've got 7 minutes total to go, everyone. So let's see if this is the last one or we squeeze one more. Go for it, John, to start.
So this is in relation to Amanda's comments earlier today about oxidizers. So, and as you just mentioned, it's like, okay, what strength oxidizer are we talking about? Are we dealing with, nitric acid? Are we dealing with, something that hydrogen peroxide, I think you mentioned earlier as well. What's the concentration? Because they all fall into different oxidizer categories. And then understanding from a hazard standpoint what the result can be, when you're dealing with, say, even a class 2 oxidizer, but certainly class 3 oxidizer. Where is it stored? Is it in proximity to flammable liquids? Because that's a definite incompatibility there. And there have been some large-scale fires, in fact, that have resulted when we have a leak of a class 3 oxidizer, and it basically, by definition, it increases the burning rate of combustible materials nearby. So it could be equipment, could be, other goods, but it could also be that it interacts violently with an incompatible material.
Great. Yeah. I don't think we got into compatibilities as much as we had planned on, but these things never go as planned. Katie, I think I'll go to you next, and then Amanda, and I hope we get time for at least one more question because I see one that we have not touched upon yet.
Yeah. I don't have too much experience with hydrofluoric acid or even HF, right? Not in the aqueous phase. There is, And so I guess I really can't speak to that too much. And this is a true story. When I was in grad school, someone had left behind a hood that had HF waste in it. And when I left grad school, that waste was still there. Right? It was just still sitting there. No one wanted to engage with it. And so I do know that if you're going to be handling HF, that you really need to do a thorough hazard review and bring in people who are experts in industrial hygiene, from your EH&S, kind of pool of experts to ensure that not only kind of from a reactivity and side that that your chemistry will be safe, but also your potential exposure.
Great, very good. And Amanda, anything in this space, nitric, acetic, HF, or take your pick? And I think we will have time for at least one more.
Well, I might loop in a bit of an answer to one of the questions I saw in there earlier that was about gloves as well. I don't know if that was the question you were going to go for as your last one.
It wasn't. So if you want to touch upon that real quick, go for it.
All right. So with nitric acid, probably one of the things that stood out to me most about it was that if you go through SESs for different percentages, 30% versus 70%, that there's just such a huge difference between the two. And if you've got percentages in between, trying to figure out where it's going to fall, as far as what changes in PPE you need to make, because with the smaller percentage, at the lower percentages, it doesn't really react with the nitrile gloves that strongly. You can even have that be, I mean, it's got a certain amount of breakthrough time, like you would want to change them right away if you got anything splashed on your gloves, but it's not like an immediate thing like those higher percentages. And it really only sets the gloves on fire, I think, when it's at like 80%, 70%. It doesn't quite do that, but it'll still degrade the material. And so it just kind of sits in an awkward area. But there are glove compatibility charts, and fortunately most of them do sort of outline, like you'll see different percentages of certain acids listed on there at various points, saying whether you need this glove type for this concentration of it. There's also some glove types that are double layered. They'll have the nitrile and the neoprene, and just FYI, chloroprene and neoprene are the same polymer. I guess they just seem to have different brand names, but they have the same chemical resistance as the same polymer.
Okay.
And go ahead.
I'm sorry, I was just going to say that nitric acid, I can't believe we didn't say anything about this, but just don't ever mix wastes. I mean, mixing waste is a bad idea, but nitric acid is the classic example. Even in relatively low concentrations in organic, a little bit of nitric acid can quickly oxidize the organic to a bunch of like carbon dioxide gas, and then you'll also get NOx gases, NO2, NO gas, right? So toxic gases, right? Overpressure your container, right? So I never mix waste, but also really never mix nitric acid waste with anything.
And I see Amanda smiling, and I wonder if she's thinking of the same lab as I am at ASU. Where there's a picture showing, this thing exploded, and it was a waste container under a bench, and only for the, luck of whatever you wish, universe, God, take your pick, had the PI already gone past it and into their office, and it exploded shortly thereafter. Had the timing been off by mere seconds, I don't know what would have happened. It would not have been good at all for him. They were very fortunate. Yeah. All right. So the question, it's from a colleague and previous panelist, Jeff Foysel, whom I know. And so he said, can you use, and this is an acronym, SMILES. Maybe it's a process, maybe it's a software program. I'm not familiar with.
Software.
Thank you very much. A good educated guess, I guess, right? To identify reactions that may be possible programmatically. So John, since you were the one who identified it, I'll let you go first, and we'll see if we have time for the others, of course.
So I have not personally used SMILES, but I am aware of similar type tools, and I would say yes. I mean, just in general, that something like that would be excellent for, pre-hazard assessment, to be able to walk into a PHA with at least some knowledge of what, what we can predict, for, what is this reaction going to do?
Great. I don't know which way to go. Katie, I guess I'll go, and then Amanda again.
Yeah, I think the answer is yes. I don't know where this is being done at a really broad or kind of usable to like a normal researcher level. I do know that there's quite a bit of kind of still Benson theory group research going on in chemical engineering programs to help understand the possibility, right, or spontaneity of different chemical reactions, mixing different materials together. But as far as if there's anything that's readily available that uses Smiles notation to predict possible chemical reactions, I don't know if anything like that is available, but that would be great if it were. If anybody on the line knows about something like that, then please put it in the chat.
Yeah, and there's been a lot in the chat, but there's been a ton in the Q&A that isn't all questions. A lot of people providing information, comments, thoughts, suggestions, of which we appreciate everything. Amanda, you will have the last word on this, and I'll just close us out when you're done.
Well, I just posted in chat a couple of sites that I use for assessing reactions. I'm not familiar with Smiles, but when I was in grad school, we used SciFinder. That one is usually, like your university needs to have or somebody needs to have a subscription to it. So it's not a free resource, but it's got a really good, it has a structure editor in there. So you can just draw your molecule and then draw another reaction, a reactant, or you can draw a product and look at, reactions that will get to that. And it's a really good searchable database for molecules. You're able to search papers by chemical structure. So that's pretty handy. And the other thing I use and this is a free tool, is Cameo Chemicals. That one's from the government. I can't remember which department it is, but
NOAA,
yeah.
Exactly.
And you can type in, as long as you have the name or the CAS number of a chemical, then you can search by that, and then you can see what its reactivity is with any other reagents that you want to plug in there on the list.
Yeah, that's great. And I copied something a friend and colleague of mine, Neil Langerman, put into the Q&A. And so I posted it in the chat, since people are really doing that quite a bit as well. And Michael closed out. Look up the book Ignition, exclamation on rocket fuel and pyrotechnics. If it's in there, watch out. Well, I will say, having dealt with a solid rocket motor deflagration, and I learned that difference, John, doing that investigation and multi-year follow-up from some absolutely brilliant undergrad students who all have gone on to do wonderful things, that even things that you've done 50 times before, occasionally things can go awry. In that case, the motor exploded, no one was hurt. Lots of precautions. They were behind a concrete bunker. Took out some stuff like a car tire and bits of building, and et cetera, but no one was hurt. And a good lesson learned. What was it? Due to avoid, in the solid, if you know anything about solid rocket motors, due to avoid it, and they wrote a scientific paper on this and submitted it to I will just say, a very large rocketry firm that you would all recognize if I mentioned it. It developed resonance. And if you know anything about resonance and the bridge in the 40s or 50s that fell down due to resonance from wind, resonance is not a good thing necessarily. It will take stuff apart. We are past the stopping point. Thank you so much to everyone that stayed with us. We still have almost 100 people. Our three panelists, thank you so much for your expertise. So many people posted in the chat. Thank you for the wonderful commentary and questions and answers and discussion and conversation. I feel like we could just keep going on forever, but I have a feeling we all have something else that we've got to attend to. So From everyone here on the risk mitigation team at BioRAFT, from our 3 panelists as well, thank you all for coming. Appreciate everything and looking forward to seeing you at future webinars as well. Everyone, have a great day and try to assess risks appropriately. It's a challenging thing to do. All right. Take care, everyone. Bye-bye.